Perfect.
Go ahead.
All right, perfect. Yeah, thank you. Thank you for the intro, and good job, James, going over, giving that full overview and talking about LibreBMC and the DC-SCM. I'm going to be diving in deeper into these two projects, basically, and talking about some of the details and giving you a better update and more ways you can get involved. So we did just have a successful event there in the OCP Open Compute Platform Summit, and we showed off this our solution, and I'm going to show you a demo at the end of how this, what our solution does and how it boots. And there was a lot of talk there on DC-SCM as well, and I'm going to give you a little overview of what that is and what's going on there, so you can get involved with that as well, if you like. But let's start with the LibreBMC. And the goal originally of the LibreBMC project was to prove that you could take an FPGA and replace an ASIC for the BMC function, the baseboard management controller function, and prove that it was performant enough to boot a modern computer system. And a lot of people, even at this at the booth there, were kind of saying they didn't think it could be done, and we would show them the demo that in fact it can, and it does work. So I'll bring you through what we've done, and then show you how you can contribute and get in and hack around as well if you are so inclined. So the goal again was to take this to boot an AC922. That's the supercomputer node that was running at Livermore and Oak Ridge and part of the Sierra and Summit supercomputer clusters. So we wanted to take the existing BMC card that had an A-Speed chip on it and replace it with an FPGA, running everything completely open. So it's using the Open ISA, the Power ISA. It is running Microwatt, which is the open core based on that ISA. All the peripherals are open. Most of them incorporated with LiteX, some not, but all open at any rate. And then the OpenBMC firmware on top. And one reason why we chose the AC922 is that it's like the only open platform. So above, as it exists at Oak Ridge and Livermore, everything is open. So the OpenBMC stack is what's used. Above that, what in Intel system they would call the BIOS, we call host boot. That's all open. There's a self boot engine on there that boots everything. All code is open. There's not a chip controller on there that does the power and thermal management. That's all open as well. So now you have a complete system. All the firmware is open, and even the hardware, if you will, that FPGA image that runs the computer as from the BMC perspective is open. We also wanted to incorporate this emerging DCM and DC-SCI standards. Those are standards that are attempting to modularize the computer systems and standardize around the connectors, like the connection from the BMC card to the planar. And again, I've got some pictures on that I'll show you later. But that standard is getting a lot of action out there in the industry. So the advantage, James was alluding to, the advantage of all this openness is one big one we focus on here is the security, that if you would have a problem out there in the field, if you imagine a Spectre meltdown kind of situation, I understand that was on actual core process at BMC, but if you had that, you could just roll out a new image and fix it. You wouldn't have to have costly software workarounds, which they had to implement until they could get the new hardware out there. And if there are new security just in the future, you can just add those enhancements by rolling out a new FPGA image. I think it is the right direction using FPGA. I think it reduces your attack surface. It doesn't completely eliminate it, because there are certainly some parts of an FPGA that aren't gateware, but it's a step in the right direction that we, as Open Power Foundation, believe should be the industry direction. A little more detail then on these interfaces. I drew this back long ago when we were designing DC922 from the beginning, and here I show this BMC in the middle. That's really the A-Speed AST2500, and it has the standard connections that any baseboard management controller would have out to like power supplies and fans. It has a connection to host. Here it's LPC up to the P9. Then we use FSI. That's unique to IBM, though we did open that up. That is now an open standard on that. So you talk to the on-chip controller via the FSI interface going through that subboot engine. So you've got basic block diagram for that AC922 node. Step one was to attempt to boot the AC922. Forget DC-SCM for a minute, right? Hadn't really, we weren't there yet. We're just trying to figure out, can an FPGA boot the AC922? Not even running not even running fully OpenBMC code, actually, but just running, just using an ASP, or I'm sorry, just using an FPGA. Okay, so this picture is actually before you do the FPGA. So you've got the box elder card, the AST2500, everything's OpenBMC going across the interface and booting that AC922 and doing all the monitoring of the fans and power supplies. So I got ahead of myself there. Then the next page here is where we did the box RD. We took the A-Speed chip, took it off, put the FPGA on it. We were running the microwatt, and we're running the Linux kernel, but it doesn't run OpenBMC. It uses some scripts to boot. It's a great first step, but it doesn't really prove the concept fully. It shows you can boot it, and we did boot the system. We got it running, and you could monitor fans and control them, but no DC-SCM. We're still using that Molex 240-pin connector. Now, for some context, it's always nice to see what I'm talking about, not just cartoons. This is the carrier right here on the right that it contains that box elder card. That there is the AST2500. This is as shipped to Oak Ridge and Livermore, and then we can see that 240-pin Molex connector on the left. We took that out. We made a board, put that Artix A7 on there, loaded the code on it, and there's the bottom, shows that Molex connector. We're able to put it in the system where it is installed, and okay, and then I should just say, and it booted it. Fans were being controlled, talked to the host, but not full function, not full OpenBMC stack running. So now with that said, let's segue from there into the DC-SCM standard and why people are first what it is. If you look at the left, this DC-SCM card, it has the BMC that would be the A-Speed in our case. They have room and designed in for a CPLD to serialize some of the GPIOs that go across the connector. The goal here is to define this connector in such a way that you can use sort of any HPM board. You can imagine an ARM or an AMD or an Intel or a Power or whatever based HPM board by some vendor. You could take that, you could take a separate DC-SCM card that has its functionality and plug those together. And I think the dream of plug and play and it just works is probably a bridge too far, but you can plug it in and electrically it would connect. You could go out and detect what HPM board do I have out there, and then load BMC code on that would then make the system operate correctly. Well, the reason people are doing this is there's a number of reasons, but one is for the ability to have a heterogeneous system. You could have a single DC-SCM card, and they could again have a number of different computer architecture, computer architectures supported. That would be cool, and in a frame. And a lot of people were talking about that at this conference. This whole composable computing, and that really is a direction that we're going to go. The standard isn't there yet to support that, but we're close or getting there anyway. And the other thing is, if you take this DC-SCM card, if you have your own and you plug it in, or you put your own code on it, now it can fit more easily into your ecosystem. So you imagine a data center operator, and they're buying computers from all kinds of different people. They plug them in, and even if they support a really nice standard like Redfish for all your systems management, there's going to be differences in how those systems are operating, and you have to have special code that says, oh, if I'm attached to this, then I do this. Attached to this other server, I do that. But if you had your own BMC code running, it could abstract that. It could always make the system look the same out to the external systems management controller. And another huge advantage is you have your own security solution. On here, you would imagine there would be a root of trust. In fact, I'll show that on the next page. So here that you would have a root of trust chip, a TPM chip, and you can design your own solution that you trust as a data center operator or as a cloud provider, right? You'd be able to buy this compute, and these things are just going to become more commodities. You buy a compute board, you take your own DC-SCM, you plug it in, or maybe you buy the DC-SCM, whatever, and then you can enhance it to have your root of trust solution and your security. So here you see a set of signals going across this DC-SCI connector, very similar to the ones I was showing for the AC922, because most computers, they do the same thing. They need the same types of connections. They don't all use exactly the same connections, right? The power systems don't use PECI. Intel uses that as an interface. So there are differences. And one thing that we needed to keep, do going forward is take this SGPIO, which is, again, that serializes. So if you have maybe 10 or 20 or 30 GPIOs that do various things, that's just a general purpose IO pin. You can then serialize those through this and only have a serial connection going across, and you have it deserialized on the other side and get that connector down in size. So there's a lot of talk. This is a rich area going forward in the future. A lot of companies are doing it. A lot of companies are participating. That'd be a good thing to get involved in, and help steer it or hack around, provide your own ideas. It's a very interesting project. So we wanted, again, to use this DC-SCI and DC-SCM concept. So we took this, we took the DC-SCM card, Ant Micro built that. There's, again, an FPGA on it, an RX-A7, and we loaded OpenBMC code and used the Power ISA and microwatt, but we could not, plug that card directly into our planar because we didn't have support for the DC-SCI connector. We built the system long before that. So we built a custom interposer. So you'd plug the DC-SCM card into the interposer, that goes into the planar, and then voila, it should work. So there's the interposer card that we built to accommodate that. There's the DC-SCM card. I showed you on the first page. There, they plug together. It's not quite perfect. This is not production ready. You can't purchase this. This is more of a proof of concept. So we'd have to modify this to make it a saleable product, which we're not interested in doing. This was just again, proof of concept to show it can be done, and we think this is the way the industry should move towards FPGAs. And we're just helping do that because we have a nice open platform to do so on. There's that card installed in the carrier, and then I showed you at the beginning the box elder card. Well, now it has this DC-SCM card in there, and yeah, it ran, booted, and all the code was running, full function, and really proved to some people that this can be done. And because most people thought it couldn't, actually. Everyone we talked to didn't think an FPGA could be performant enough, and just didn't believe it was going to work. The other people have other reasons why they think we shouldn't use FPGAs, cost and reliability, but I think those are sort of going away as well. So I will now switch and show you the demo. 1 second. All right, here we go.
We'll be booting for this demonstration, we'll be booting a microwatt BMC and then using that to boot an AC922 server. Our setup on the screen here is 2 consoles, one for the host server system on the left and one for the BMC on the right. To get going, we'll reset the DC-SCM and microwatt will start the boot process. Pausing here for a minute, this is the early boot output from microwatt. It'll print information about the gateway build, start initializing DRAM, and then start the U-boot bootloader, which then starts our Linux kernel. We're running through the boot process a little faster than real time here, just to save viewing time. The microwatt core is running at 100 MHz. Even though it's a fraction of the clock speed of our regular BMC, it's still sufficient for reasonable BMC performance. We'll start user space code about 20 seconds in from boot. The kernel will then start our OpenBMC user space, which is loaded from the onboard eMMC storage accessed through Light SD card gateway. The user space code we're running here is a port of the AC922 OpenBMC implementation, which was originally an ARM system, to the DC-SCM microwatt core. As well as the change in core architecture, this port also needs a set of system-on-chip peripherals to support BMC functions, like GPIOs, I2C interfaces, and an FSI controller to interface to the host processors. Some of these, like the I2C and FSI interfaces, are software implementations, so we do have future opportunities for optimizations by adding these as gateway components instead, reducing the load on the microwatt core. Now that the system is booted, we can log in and take a look around. Proc CPU info shows our microwatt CPU. reporting as a 64-bit PowerPC architecture. We also have a set of I2C buses present for communication with the various devices on the platform, like thermal sensors, fans, and I/O expanders. There's also a set of general-purpose I/Os defined in Gateware Linux for direct platform signaling. Since we're using software bit banging for the I2C and FSI controllers, we have GPOs defined for the clock, data, and control lines of each interface. Of course, we have a network interface too for remote control of the BMC system. This is implemented as Light Gateware plus a simple Linux network driver. Over on our browser now, we can access the OpenBMC web interface. For this port of OpenBMC to microwatt, we've not needed to modify much in the upper layers of OpenBMC infrastructure, just the interfaces to underlying platform hardware. Once everything is loaded, we have the standard OpenBMC web interface, showing some base server system information. This is currently reporting a health issue, so we can view the event logs to see what might be causing that. Here, we have a few events from a previous boot, which we can clear out. Once doing so, the health status shows we are back to normal. We also have access to the system sensors through the web UI. As part of this port, we haven't yet implemented the full set of platform sensors, but we do have an initial set available. Using the ambient temperature sensor as an example, you can see it's about 20 degrees Celsius in the Bring Up lab here. Back at the full sensor list, since the server is still powered off, the fans are reporting at 0 RPM. Full fan control will be enabled once the server boots. Over on the power control interface now, we have the current server power status, indicating that the platform is off. We also have the usual BMC type settings to configure boot behavior. Our plan here is to demonstrate a boot of the AC922, so we'll start the server power on operation and get the system running. After clicking the power on button, we'll flip back to our console windows. In the BMC console on the right, we'll follow the BMC logs to see it perform the boot procedure. In the terminal window on the left, we'll connect to the host console by SSHing to port 2200 of the BMC. This is a network accessible channel of the host serial output. As the BMC goes through the system boot process, we see quite a few messages from the initial power on stages. As a rough overview, the BMC is configuring for the host power on state, starting the power supplies, fan control, and then we'll configure and start the host processes. We do get a few warnings in the log output. Some of these are expected, others are due to the prototype nature of this platform port so far. At the end of the power on process, the BMC will start the SBE, or self-boot engine, on the main processor, and then the rest of the server boot procedure occurs on the AC922 main processors. Now on the left-hand side, we can see the serial output from the AC922 host as it comes up. First, we have the SBE output, and then host boot, the second stage of the Power 9 platform boot. We're going through the host boot procedure a little faster than real time again, just so we're spending less time watching console messages fly past. One last stage of host boot is to start the OCCs, or on-chip controllers. The OCCs interact with the BMC for full thermal control, and we can see the BMC detecting the running OCCs here. Once detected, the BMC will establish communication with the OCCs, giving the BMC access to a further set of thermal and power sensors. Once OCCs are running, hostboot will then start the runtime firmware called Opal. Opal will perform more platform initialization, like enumerating PCI devices, and establishes a suitable runtime environment for Linux. Once Opal has finished its initialization, it then loads and runs the Power 9 bootloader, PettyBoot. PettyBoot is a small Linux-based system which probes for operating system installations on any attached storage or network devices. In this case, PettyBoot has discovered the Ubuntu installation on this machine, and then, after a short countdown, will load and boot it. At this point, the BMC is no longer involved in the platform boot process, as the main processes are now running independently. However, the BMC is still performing the usual runtime monitoring and sideband management tasks of the platform over the FSI, I2C, and LPC interfaces to the host. After a short boot process, Ubuntu is up and running, and we have a login prompt on the host. Here, we can log into the running Power9 system and take a look around. Proc CPU info shows our Power9 host processors, and, like the BMC, this is reporting as a 64-bit PowerPC architecture. However, in this case, we have 128 of them running at 2.3 GHz, rather than our 1 microwatt CPU on the BMC running at 100 MHz. In this project, we have ported the open source OpenBMC firmware for an IBM AC922 system to an Antmicro DC-SCM module running microwatt gateway controlling a full Power9 host system. All components of this BMC implementation are open source. The DC-SCM hardware design available on Antmicro's GitHub repository, the microwatt PowerPC CPU implementation and peripheral gateway, the Linux kernel port, and, of course, the OpenBMC firmware components. We have links to the source in use for this port available at the URL shown, and would like to thank the Open Power Foundation and IBM for their support in this project.